Okay, so my goal will be to present the goal of these 5 lectures, but before I could just start with theorem and then start the proof. I feel like I need to maybe motivate and tell you a little bit of a story about why you should even care. And I think in general, especially for the young people in the audience, please always tell people why they should care about the work you're doing. They may not buy it, but you have to try. Fundamentally, the problem that I care about is the same that the one Jonathan cares about, namely turbulence. Except Jonathan's talks have been focused mostly on two-dimensional turbulence, not because any of the methods care about 2D, it's because we have good estimates. The methods, of course, don't care about dimension. And what I care about is mostly about three-dimensional turbulence today. And by that, I really mean what is called fully developed isotropic turbulence, as was coined by Jonathan's academic grandfather, Mr. Komogoro. Today, I will basically try to give you a flavor of what one can measure in turbulence according to people who do experiments and also people who do numerics. There are many things you can measure, and people have been thinking about this problem since the 1920s. I will focus only on 3 things because these 3 things are, in my understanding of the subject, unquestioned, to the point where people call them laws, meaning nobody doubts them. And so I want to start with that today. And then slowly we're going to shift to more math. But today is going to be a lot about. So we're going to start by writing the Navier-Stokes equations on the board. Now let's write it in velocity form. And of course, in this talk, I care about incompressible fluids. So these are the Navier-Stokes equations. And because in the end, I'm going to want to send the viscosity to 0. Maybe I should decorate these with a little nu upper index to emphasize that they depend on nu. So the picture is the usual one. You pump in force at low mode, be it deterministic, be it stochastic, and whatever I'm going to talk about today, it's going to be deterministic, but it doesn't really matter. You compute the solution. At the end, you have some observables of the solution. And I want to tell you a little bit about observables today. Nu here I'm representing as the kinematic viscosity, but of course you should really understand this as 1 over the Reynolds number. Okay, so I don't want to carry units. So I've already done from the physical system where this has this kinematic viscosity and this has units of length. I've gone to non-dimensionalize everybody. So this is really 1 over Reynolds number. And then I've gone back and I've called 1 over Reynolds number nu. Okay, so nobody has any unit. The first thing I want to say is this equation has an energetic structure. And this energetic structure relates to the kinetic energy, which is 1/2 the integral over the box. Oh, everything I talk about today will be on the unit box with periodic boundary conditions. I'm assuming that the force has 0 mean. So if you start with data of 0 mean, it will remain of 0 mean, essentially because the nonlinearity is in divergence form. This nonlinearity can be written as the divergence of this. So it's in divergence form. So the mean stays 0 if you start with it 0. So all solutions which have 0 will have 0 mean. Yes.
Because I see the screens which are low.
Oh.
Why don't we fix the screen? Let's call in the expert. We're calling in the expert.
Thank you.
This is a
Is he the expert just because he's tall?
Yes.
It's off. It's off.
No, it's not going to say it that way.
It's all right. It's all right.
Just get a new piece
So at least I can't complain that I didn't have coffee like Jonathan. This is just what I do. So before I tell you about the energy, I just want to say one thing, that you will not hear me say much about the pressure in this talk, because always the pressure is one thing and one thing only. Take the divergence of this equation, and you get that the Laplacian of the pressure is equal to the divergence of the force minus div of the nonlinear term And this, if you impose zero mean, always has a unique solution on the box, and the pressure is always that. Okay, so you will never hear me say anything about the pressure because that's the pressure. It's a quadratic function of velocity and the linear function of the force. By the way, the force really shouldn't be written as F. That's kind of stupid. You should always write the force in divergence form. R stands for Reynolds stress. We'll talk about it. Anything of zero mean is a divergence of somebody, so I didn't really do much. Okay, so energetic. So the kinetic energy is 1/2 integral over the box, let's say the mean of the L2 norm. And the energetics of this problem say that the time derivative of kinetic energy, well, at least for smooth solutions, from the Laplacian, you're going to get S integral gradient U nu squared dx. Let me not write the T and X dependence, okay? From the stress, you're going to have plus integral. You can write it in either way. Let me leave it like this. Pressure. So what am I doing here? I'm taking the dot product of the equation with U nu. Integrate a gradient against a divergence-free object. If everybody is smooth, that's zero. Okay. So the pressure gives you no contribution. And you have one more term from the nonlinear term. Write it in coordinates. So you have U nu j dj U nu I ui. Sub I goes from 1 to 3. dj really means dxj. And obviously this is the same as dj of the length of U nu squared, 1/2. So I can integrate by parts if everybody is smooth. So I get a plus here. And if I integrate by parts, I get the divergence. So if everybody's smooth, this is the energetics. The derivative, the time derivative of the kinetic energy is equal to the energy dissipation rate due to the Laplacian, due to friction. This eats energy. And how much energy you're pumping in through the force. And there's a balance of this, okay? And this is called the energy balance. If your force is decent, or is an L2 function of time, let's say, values in H in L2, then this automatically gives you a priori, the a priori estimate that U nu is uniformly bounded in time with respect to L2 norm in space, and it's square integrable in time with respect to the H1 norm in space. The dot just means that it's the homogeneous H1 norm, although since everybody has zero mean, the a priori estimate only depends on the data and this norm of the stress. That's the a priori estimate. So this is a good, this is not a good, but it's a natural regularity class to work in. I have made several assumptions without spelling them out. I've integrated by parts many times. And so you should really wonder, this space, these functions in here are not very smooth. So if I tell you that the solution lives in the natural space, is the computation I did to get that the solution lives in this space, is it even just? So here's the correct computation. So if U belongs to the energy space, instead of writing everything in integrated form, please let me write it in the sense of distributions. Then you can prove that dt of U squared over 2. Okay, so I'm really writing distributions. Plus the divergence of U times the Bernoulli pressure minus nu gradient. And let me not write the upper, okay, let me write it since let me not be lazy. Equal to minus nu, well, yeah, let me write it like that. Minus something which is called d nu nu. So this is the only thing that you haven't seen on that slide, because and of course the force plus U nu dot div r. So if I integrate this in space, of course, everything which is a divergence dies. And this term, and this term are the three terms that you see here, 1, 2, 3. And there's a 1, which I called 0, which now is sitting there explicitly. So this is a measure, a dissipation measure. And it's written, it's an explicit thing. People in turbulence call this the Karman-Horvath-Monin relation. Basically, for any function u, this measure associates the following object to u. So it's going to be the limit as little l goes to 0. This limit is to be understood in the sense of distributions. So what I'm having on the left and on the right side of the board are distributions of t and x, okay, of 1/4 integral over the box of, let's see, gradient of a modifier evaluated at z, dotted with the increment of u in the direction z, delta z u squared dz. And the only thing I have to tell you now is what is phi L and what is delta z. Delta z is an increment. So delta sub z of u as a function of t and x is just u of t x plus z minus u of tx. It's the increment in the direction z. And phi sub L is a standard modifier. So phi L of z is L to the minus 3 phi of z over L. And phi is a positive, compactly supported, even bump function of mass 1.
Is there something extra under the divergence?
There's something extra on this.
Yes, you have the Laplace.
Thank you, Dallas. Thank you. Yes. So again, this is just a mass 1 positive even. Energy dissipation measure is associating to every function which belongs to where? Well, it better be at least in L3 space-time. Otherwise, you can't really make sense of this. So to even write down this measure, I really need that U belongs to L3 space-time. Otherwise, I cannot even define this measure. What this measure is encoding is the possible additional loss of energy due to roughness. Okay, so let's ask ourselves a little bit. If U is a smooth function, well, if U is smooth, then delta Z of U scales like Z, right? Because it's an increment. So by Taylor's theorem, I should get a Z out of this. Out of this one, I should get another Z, Z cubed. Well, the gradient on the modifier costs L inverse. The moment of the modifier gains you 3 powers of L. So if Z is smooth, not only does this go to 0, it goes to 0 like L squared. So this is a very zero object. When is this not equal to 0? U is a Berger's shock. I guess homework 1. Oh, by the way, throughout my lectures, there will be homeworks. And you have to submit them to Jessica. And I'm going to grade them. And you're going to get reimbursed depending on your homework. So homework 1.
Reimbursing us for our time here? Or what are you the reimbursement for full time? Yeah.
Let me not continue. Take this function. Please rewrite this in 1D. So change the 3 to a 1 and change that to a 1. Take that function, which is just a step function, which naturally arises in compressible dynamics, and prove this is a homework 1. Oh, 1, sorry. This formulation, Shaw and Robert, it's a really elegant paper. I think it has 6 pages in total with introduction and references. And the proof of this is half a page. It's super elegant. I strongly encourage you to look at the paper of Shaw and Robert. This is really half a page. It's beautiful. It's what beautiful math should be. One thing I want to say before we continue, by interpolation, normal interpolation, you get that U a priori belongs to L 10/3. So in particular, just by doing interpolation of these spaces, you get that in 3 dimensions, this is like L6, right? By Sobolev embedding, and then you do L infinity L2 with L2, L6, and you get this, okay? In particular, 10/3 is more than 3, so this number is okay. So we are allowed to even talk about this subject. Okay. So now I promised you that I would start with turbulence. So let us now finally get to the point. The reason I wanted to write this to you is because we can finally define the energy dissipation, this and this, except, as I wrote it now, it's a distribution. Maybe we should do an average. And now comes the magic bullet of statistical physics. This average is really meant to be maybe the averages that Jonathan was talking about, average with respect to the unique ergodic invariant measure that you can actually maybe prove in 3D if you're smart enough. Not me, of course. And that's what it could be. In our language, okay, what happens in a lab? In a lab, you just see one experiment. The only average you can do is average over a long time. You can watch that experiment for a very long time, and you can do 1/t integral 0 to t of whatever, okay? Now, in a numerics thing, what you could additionally do is maybe you could average over the box because you have all the information. So let's slap that on top. And in addition, we'll see that we could do one more average later on. This z here is an element in R3. But when we were talking about whether this is 0 or not, it's really the modulus of z. So if you're writing z as modulus of z times an element on the unit sphere, we could also integrate over the unit sphere. That's where the word isotropic in isotropic turbulence comes from. Okay. So this is the energy dissipation, the average energy dissipation rate that the fluid experiences. And again, the word average here could mean either this. Ideally, there should be no ambiguity. We should have ergodicity. We should have mixing. And then there's no ambiguity about what this average means. Okay. The first, or the so-called zeroth law of turbulence, according to Srini, is that lim-inf, as the Reynolds number goes to infinity, of this energy dissipation rate is not equal to 0. So you see there's a nu there. We're sending nu to 0. So if everybody is smooth, this goes to 0. If everybody is smooth, this is equal to 0 without even sending nu to 0, right? So this should be 0 like from the get-go. But the fact that this is not equal to 0 is the zeroth law of turbulence. So this is called anomalous dissipation of energy. This is somehow the building block of all phenomenological theories of turbulence. And in particular, nobody questions this. You simulate Navier-Stokes, you get this, it's true. You watched an experiment, you get this is true. This is the reason why many things in real life happen. This is how stuff gets transformed into heat. I want to make one mathy comment based on this observation. If this thing that we're seeing in experiments is really to be trusted, and I do not believe that all experimentalists are liars. I think they're pretty good, actually. Uniformly bounded in a Banach space, which would ensure that this goes to 0. Maybe I could just tell you the answer, but I have to motivate it, and I'll motivate it later. The answer is L3 in time, best of space with index S, 3 in infinity, with S more than 1/3. So let me write the norm down. So let me write U in BS3 infinity. The norm is just the L3 norm plus the supremum over all Z positive of 1 over modulus of Z to the S, and then the L3 norm of the increment, right? Just that's the Bessel norm. And this 3 refers to that 3. This infinity refers to the sup, and the regularity index is there. So in particular, the sequence of solutions of Navier-Stokes cannot remain uniformly bounded in this space because, as we will show, if you are in this space, this limit should be 0. And as a consequence, we shouldn't be studying strong solutions, smooth solutions of the limiting system. So when I say limiting system, what is the limiting system? Formally, it's the Euler equations, the incompressible Euler equations, where you just set viscosity. Euler equations, you just drop the viscous term in that term. So if you were to study, quote unquote, turbulent solutions of Euler, you better study weak solutions and not smooth solutions, because weak solutions simply are able to capture the anomalous dissipation of energy, whereas strong solutions cannot. Now, in addition, you may want to study weak solutions simply because singularities happen. There are recent works of Tarek El-Gindi, Tom Howe, and Jia Chen, etc., who actually prove that singularities do happen in certain scenarios. So weak solutions for Euler is the way to go. So this is the first thing that you measure in turbulence, and that's unquestioned. And the next thing is about structure functions. Okay, so let me first define these objects. All right. So let me define first longitudinal structure functions. Two indices. The parallel refers to longitudinal, and you can write perpendicular. The P refers to a moment, a pth moment, and the L refers to a length scale. So this is going to be the average in time, well, average over the box, average over S2 of is associated to a solution. So U nu of T x plus L z hat minus U nu T and x. So I've just rewritten the increment, except I've split the modulus and the direction on the unit sphere. I wrote them separately. I was alluding to this earlier. And I'm going to average the z hats. Okay. Now it's called longitudinal because you don't just look at this increment in absolute value, but you look at it in the direction of z hat. And you take the pth moment, and you do dz hat dx dt. Longitudinal structure function, and if you want to add the adjective longitudinal, I would just remove this dot product with z hat. So if you want to talk about absolute structure functions, same thing, except I don't dot with z hat, you just put absolute value. The pth moment of a certain object. You may wonder how this pth moment depends on two things, of course, on p and s. You always do in physics. You assume that the dependence is algebraic. So you maybe assume it's a power law. And if you want to identify this power law, you may want to take a log of this, divide by log L, and see what you get. Of course, you can't take log of objects which have units, right? That's illegal. So you need to take log, the correct thing to do. These are, okay. And you want to look at the limit as L goes to 0. Now, there's an implicit dependence on Reynolds number in everything. There's a nu floating around. Let me draw you a picture. If you are given a Reynolds number, Kolmogorov theory of turbulence determines that there's a length scale. It's called a dissipative length scale, after which molecular friction dominates and nothing really happens. So what is plotted here is absolute value of Fourier mode. That's why small length scale mean very high Fourier modes, so they're there. Okay. This is the length scale where you pump in forcing with your R. This thing in the middle is called the inertial range. I'm writing here, I'm implicitly assuming that I'm looking at it in the inertial range. Okay, I'm always implicitly assuming this without saying. So you may want to give this a name, zeta sub p, and this is the pth order, and you can do this for parallel or not parallel, the pth order function exponent. It's a bit esoteric at this point, but for the analysts in the audience, we can relate zeta p to a regularity, actually. If you really look at what this is, remember do I still have the Bessel number? Yeah. So if I know the rate at which this goes to 0 as L goes to 0, I'm essentially writing a Bessel form, right? So turns out that, that a function having structure function exponent zeta p corresponds to regularity zeta p over. I have a structure function exponent. And why is this division over p? Because I didn't take the 1 over pth root of this, right? It's just raising to the p. So the fact that I didn't take the 1 over pth root explains this division by p. Scaling analysis, you can just write zeta p equals, okay, because equals implies an equality. I really mean it's true in the inertial range. Okay, so let me use a squiggly sign to mean that. Okay. And this is epsilon L pre on 3, L over the size of the box, which is 2 pi, power zeta p, sorry, SPL, sorry. SPL, so the structure function defined here, this is how it relates to the structure function exponent. And now, finally, since I've defined all these objects, what is actually observed in turbulence? So the Kolmogorov theory, the early 40s, predicts that zeta p, that's just based on scaling. The only reasonable thing, if everybody had scalings, would be this. Now, that means in terms of regularity, that solutions belong to the best of space B 1/3 P infinity. When P is infinity, that's the Hölder space, C 1/3. When P is 2, that's more like the Sobolev space, H 1/3. And this is Kolmogorov's prediction. Now, what do you actually see in experiments? Draw on this plot the value of zeta p, and we may want to start with 1, 2, 3, 4, etc. Kolmogorov's 4/5 law says that S3 parallel L goes like -4/5. This corresponds to zeta 3 equaling to 1. There's 1 here. Amazingly, all experiments match, like on the spot. The error bars here are incredibly small. Kolmogorov's theory would say that not only is zeta 3 equal to 1, which is 3/3, but it's always p over 3, so it should be a line, right? Slope 1/3. That these should be all the structure exponents. Now, what is actually measured in fully developed turbulence is that when p is 2, so on this line, structure function exponents are strictly larger than the Kolmogorov predicted value. Not universal. You can run different setups. You get maybe slightly different values. This one, which is universal, you always get this with the prefactor. You know, that's kind of amazing. That -4/5 is not a random number. And for all p's higher, experiments show, again, not universal, bend down like this. And in fact, a recent paper of Srinivasan, Iyer, and Young, that SP goes to infinity, zeta p goes to 0, or as some of my colleagues have tried to convince me, it actually goes negative. The reason I'm saying that is to emphasize that this is the hallmark ghost of intermittency. Intermittency is looking at spatial concentrations of certain high peaked objects. Spatial concentrations are going to pick up different LP norms. And the fact that the zeta p's behave so differently for different p's is saying that turbulence is intermittent, in fact. And in addition, the fact that it goes to 0, even if it were, sorry, it goes to a constant, not to 0. Srini claims it's 2. He has reasons for this.
What did you mean by negative slope?
By negative, I really mean that if you were to divide this by p, zeta p over p would actually go negative, which I don't, it would just bend down. The point I'm trying to make is that zeta p over p goes to 0. So in particular, if you're looking at Hölder spaces, which corresponds to p is equal to infinity, the only regularity that you should expect in the limit is no regularity. Okay, you should have bounded functions, not Hölder functions. Whereas in L3, you should have functions which have 1/3 of a derivative. And in fact, in L2, you should have more than 1/3 of a derivative. Okay, so these are predictions based on simulations and experiments. I think the organizer are trying to signal me that I'm out of time. No, not yet?
No, I want to ask a question.
Excellent.
How confident are we that when p is not 3, the numerics really produce different values as opposed to always the same value, which we do not know how to characterize?
Okay, so my understanding is that we'll run different experimental setups. And what do I mean by different? Like different type of forcing at the low modes. Right? This should be independent of the forcing, right? You should forget. Slightly different forcing, slightly different boxes, give you slightly different values. Now, how confident is that? I think up to p is 6. They have the statistical confidence that they're really different. But for p very large, I think Srini in this paper claims that for p up to 12, he has the statistical confidence to say what it is. And larger, he just extrapolates, of course. But you can go to p quite large. And it's still statistically significant enough, right? Because they're not taking these averages, they're doing many runs, and then they're averaging the runs.
The reason p equals 3 is so rigid is just structural reasons, right?
Absolutely.
So
it's a quadratic,
like
it's a PD with quadratic nonlinearity.
Right.
And
Oh,
The energy is also quadratic. So when you take the time derivative of the board is trying to tell me I should write it down. Right. So the thing we had here was quote unquote the integral of divergence u tensor u plus blah blah blah. And the fact that this is cubic is why the third order moment is really special. And it's very rich. That's why p is equal to 3 is very special.
It's related to the what you call the Karman-Horvath-Monin. Yeah.
That's why I put quotation marks. I should rewrite d of u here. This d of u. Okay, which board am I on? I had prepared for you predictions. So Srini claims that in his experimental setup, zeta 2 is like 0.71 plus minus 10 to the minus 5, more than a third. So these are these numbers, more than a third, more than 2/3. I'm sorry.
But then here you produce one number.
Yes, and if he's running a slightly different setup, he produces a different number. He had one setup, and he took many data, and he averaged over the data. And it's super expensive because it's apparently 10,000 cubed simulation. Okay, I just want to say one more thing about intermittency refers to the fact that zeta p is not equal to p over 3. There are models that people try to produce. There's one famous model from the early 70s of Frisch and Sulem, which is called a beta model. Sorry, of Nelkin, Sulem, and Frisch. It actually says that in rough terms, you have one big vortex, then this vortex splits into 2 to the d many vortices, where d is like a dimension, which is a real number between 0 and 3. So 2 to the something between 0 and 3. Then this vortex splits into 2 to the d many smaller vortices while conserving mass. And this fact that they always split into equal number many is called sometimes monofractal theory of turbulence, because it's really a monofractal. And the beta model predicts actually, so zeta p in the beta model is going like this d that I kept on referring to. This d is a number between 0 and 3. Obviously, Kolmogorov's theory corresponds to d is equal to 3. And this is why Kolmogorov's theory is referred to as fully developed isotropic homogeneous turbulence. It's not just in all directions that it's the same, it's also everywhere. So it would not be able to distinguish a fractal. A fractal would mean d is equal to 3. But the beta model says, or at least this monofractal theory of turbulence, says that actually turbulence concentrates on a fractal of dimension d, where the turbulent action happens. And okay, you can take this and you can plot it, you get a different line. It's still not concave, it's still linear in p. So this is obviously not correct. It's gonna, maybe you can interpolate it so that it nails one more moment. And maybe do a least squares between the 2 and the 4 moment. And of course, Frisch and collaborators, Parisi, etc., they have proposed more complicated multifractal models of turbulence, but let me not get into this. I want to say that according to these experiments of Srinivasan and collaborators, these recent ones, he's claiming that somehow turbulence really confines itself to a 2-dimensional fractal. It's hard to imagine for me. So, and what does he base this observation on? He's basically saying that if I look at longitudinal structure functions, which look at between 2 points and you project it in that direction, or if you look at 2 points and you look at the, or if you look at, which would be the perpendicular structure function, you get very different numbers, like very different. Moreover, these perpendicular ones, this perpendicular one seems to match the absolute value one. So in particular, he's basically saying that there's something like sheets hidden in the 3D fluid, and there are discontinuities across a sheet, which are less violent than the behavior along the sheet, which would be the longitudinal structure function. He's saying that when you go across the sheet, he's somehow trying to say that if you could potentially imagine a fractal bit out of vortex sheets, that's what he's trying to say is happening. It's kind of hard to imagine this, but yeah, these are experiments. Okay, so I've spoken a lot about experiments so far. And the reason I was trying to do this is because, you know, if physics always sees the same thing, I try to prove this mathematically. Physics doesn't see the same thing, like here or there. You may have a hard time formulating a mathematical problem that you can prove. Turbulence is about real fluids, which have friction and diffusion and walls. In PDEs, we're talking about the Navier-Stokes equation and the Euler equation. These are idealizations, right? Some of these statements that you can make here, you can translate via this idealization into really statements about behavior of solutions to these PDEs, right? And one natural question would be, okay, so this is saying that on average, something happens, right? On average, it's saying that on average, this is what happens. So the question that I'm part of this program, and this program is not trying to tell you that this happens on average, that's Sam's and Jacob's job and Alex's job. We are much more laid back, and we're trying to see, can we even construct one example when this happens? So we are in the business of not saying that this happens on average or almost all the time. We're in the business of trying to just construct solutions of these PDEs which have these features. What does this prove? Does this prove turbulence? Absolutely not. It just proves that the model is not inconsistent with the physics, which is something that you may want as a starter. And this is what these lectures are going to be about a specific construction which deals with this. So the remaining 4 lectures, I'm going to try to formulate a mathematical statement related to this, and then to prove that theorem. So that's the goal of these lectures. Again, the goal is just to construct examples. We're not claiming that this is really what happens in a fluid. Although, as you will see, the more physics you put into your constructions, in quotation marks, the more chances you have of actually proving the theorem. So see you tomorrow, I guess.
So for the model you described with periodic boundary condition, etc. And if we imagine we encode these experiments, but maybe with different smooth forcings, etc. Do you think that indeed we will see different values for zeta2, let's say?
Yes. Well, I strongly believe this, yes.
Yeah, this is kind of a shock for me.
I do believe this.
So in the dissipation measure that we constructed in the beginning, there was this this Bank function.
Yeah.
So what information could you encode for different bump functions?
Excellent question. Excellent question. This measure, I wrote d of u. I didn't write any phi dependence.
Yeah.
It's the same. You can prove a posteriori that no matter which bump function, which is even of unit mass and positive, the measure is the same. Theorem.
Even if the thing you're looking at is super rough?
Yeah, yeah. That's Duchamp and Robert. Well, no, it should be C0 infinity, sorry. All bump functions, my bump functions are always C0 infinity.
Okay.
Sorry.
Is it so it's because of the isotropy of the
It's because this thing appears on the right-hand side of an equation. We wrote an equation, right, which was the energy balance. And this thing appeared on the right-hand side. None of the other terms depended on the modifier. So if this equal is true, it means the object cannot depend on the modifier. That's actually the proof of Duchamp.
Okay. Okay. Thank you.
Thank you.
So is there some, so you mentioned this 2D or the fractal structure. Is there some connection to that in sort of the spectral properties of the velocity field or Lagrangian dynamics? And it kind of seems like it's saying that like either Lyapunov exponents or the spectrum of gradient of U or something has some structure, and it's kind of squeezing into planes or something.
I think there is a connection,
okay.
But I must honestly say that I have not thought about it very much, so I would bullshit you if I would say something now.
Right.
But there clearly is a connection. And I just want to say one more thing in terms of what Jean-Christophe is saying. This phenomenon in turbulence, which is sometimes called spontaneous stochasticity, that if you force a deterministic dynamical systems with random noise, if the deterministic dynamical system, as long as it remains smooth, when you pass the noise to zero, the measures over all data converge to a point mass located on the deterministic object. Okay. After blowup, these measures have a density. This is spontaneous stochasticity. The fact that this actually happens in turbulence tells me that there's probably a measure, and these structure functions really capture the fact that this is a measure. And on the third order moment, it just collapses this measure to an object.
I mean, this is not in contradiction with the idea that zeta2 will be the same. Zeta2 is capturing some intermittency property of the stochastic object that you're talking about, but it could be zeta2 is always the same. Nevertheless, it's like
just like
one
zeta3,
random
yes.
factor.
Just like zeta3 is always the same, right?
Yeah. So
it's not in. I agree with what you're saying, but I just wanted to argue why I think, to me, it would seem natural that it's not, because there's nothing special about 2.
Yeah,
One
I
or
understand.
two,
To me,
eight.
there's some sort of stochastic object that is an attractor to these dynamics, and there's one there's one turbulent, like fully developed turbulence model. It's hard to imagine that you can produce a different
Intermittent.
local structure by turning your spoon slightly differently in your cup.
I agree. That's a very upsetting thing to think about.
So I'm still very puzzled by the idea that zeta2 would be different for different forces.
Any other questions? Thank the speaker again.
Thank you.